Welcome to How AI Models Work. In this February 2026 audio guide, we'll walk through the month's main ideas in plain English. How AI models represent meaning, retrieve information, use tools, and generate text, images, or music.
Yeah, it's going to be a fun one today.
Totally. I
Yeah.
mean, imagine finding out that the brilliant AI writing your emails has literally no memory, right? It
hmm
can't actually do math, and it doesn't even understand the words it's saying.
Yeah.
It's just this wildly fast guesser.
Which is, yeah, it's a huge shock for a lot of people.
Right. So today, we're ripping off the casing.
Mhm.
We're moving past this popular idea of AI as some, single all-knowing magic brain.
Yeah,
We really want to look under the hood.
exactly. We
Uh,
need to understand the specific mechanical workflows that actually make these systems function because it's a much needed perspective shift for, well, anyone using them.
yeah, to really see what we're dealing with.
Right. If we look at the machinery itself, we start to see that they aren't conscious entities. I mean, they are just highly complex statistical engines.
Just really good calculators,
Right.
basically.
Yeah, exactly. So, over the course of this discussion, we're going to break down what different models are actually built to do. We'll explore how they process our human language into, mathematical numbers.
Which is still wild to me, but we'll get into that.
We will. And how they retrieve specific facts when they need them, how they interact with external tools, and finally, how these exact same foundational concepts apply to generating art and sound.
Awesome. But I mean, before we can even begin to understand those workflows, we have to stop grouping every single AI system into one giant bucket, right?
Oh, absolutely. That's step one.
Because I feel like people hear the word AI and they just assume it's all exactly the same software. Like if I want to forecast my company's sales and then I want to write a poem, am I using the same machine?
You are absolutely not. And that is, frankly, the most common point of confusion out there. To sort the toolbox, so to speak, we first need to separate machine learning from deep learning.
Okay, so break that down for me.
Right, so machine learning, or ML, is the broader category. Think about traditional software for a second. A human programmer writes out every single rule by hand, like, if X happens, do Y.
Right, line by line.
Exactly. Machine learning flips that entirely. Instead of hand coding the rules, you give the model historical data and it finds the statistical patterns on its own.
Oh, okay. So it learns the relationship between the input and the outcome just by looking at the history.
Right.
So if I have like a massive spreadsheet of past customer data, classic machine learning is what I'd use to find the hidden patterns in those rows and columns.
Correct. But, spreadsheets are neat, they're structured. What happens when you have messy, unstructured data?
Like stuff that doesn't fit into a grid.
Exactly. Things that do not fit neatly into rows and columns. Think raw text, audio recordings, or millions of visual pixels. That is where deep learning comes in.
Ah, got it.
Deep learning is just a specific subset of machine learning that uses artificial neural networks with many different layers, hence the word deep.
Okay, so if generative AI is the one writing the poems and, making the pictures, what is the AI that flags my credit card as fraud doing? Is that a totally different process?
That is predictive AI, which is honestly the quiet workhorse of the entire tech industry.
The quiet workhorse, I like that.
Yeah, because it does not generate new text. It just estimates outcomes based on past data. It forecasts demand or flags a transaction as fraud or calculates the risk of a loan default.
Oh, okay.
And crucially, it outputs probabilities. It gives you a score. So, say a 0.82 probability that a specific transaction is fraudulent.
Okay, so predictive AI is basically like a highly sophisticated weather forecast. It looks at all the current conditions, looks at past data, and estimates exactly what's going to happen next. And it just gives you a percentage.
That's a great way to put it, yeah.
But generative AI is the one everyone is, actually talking about lately. That's the one creating entirely new content based on the patterns it learned during training.
Yes, and large language models, or LLMs, are the specific generative models we use for text. What's fascinating there is the mechanism of how they actually generate that text.
Right, because it's not what you'd expect.
Not at all. They do not write a whole paragraph at once or, even a whole sentence. They generate text step by predicting the most likely next token.
And a token is just like a small piece of text, right? Like a
Yeah.
syllable or a single word.
Broadly, yes. You can think of it as a piece of a word. So the model looks at the sequence of tokens you gave it in your prompt and then statistically estimates what token should logically come next.
But wait, if I ask the same AI the exact same question twice, it usually gives me a slightly different answer.
Yeah, it does.
So if it's really just doing a statistical calculation for the most likely next word, Shouldn't it give me the exact same paragraph every single time?
It would if it weren't for a setting called temperature. Yeah. Temperature controls the randomness of that next token choice. Let's say the model calculates that the next word should be apple with an 80% probability,
Yeah, okay.
and maybe banana has a 15% probability, and shoe has a 1% probability. If the temperature is set very low, the model is strictly mathematical. It will pick the 80% option.
So it picks apple.
Almost every single time, yes. It becomes very consistent and very predictable.
But what if I turn the temperature up?
If you turn the temperature up, you flatten out those probabilities. The model is suddenly allowed to pick less likely tokens. So it might pick banana or occasionally even, shoe.
Oh, wow.
Yeah, it takes more risks, which creates more varied creative phrasing. It is generating on the fly, not retrieving a fixed file.
I see. So generative AI is really more like an improvisational actor.
Yeah.
You give it a scene prompt and it produces a plausible script, line by line, just reacting to whatever was just said. But that makes me wonder, if these models are literally just guessing one single word at a time, how do they not go completely off the rails? Like, how do they stay on track for a 5-page essay without just drifting off topic?
They stay on track because of a mechanism called the context window. Every single time the model predicts the next token, it doesn't just look at the last word it wrote.
What does it look at?
It looks back at the prompt you gave it, plus all the tokens it just generated. That entire block of text is the context. It feeds the entire conversation back into itself for every single new word.
Oh, wow. Wait, so if it writes 1,000 words to write word 1001, it rereads the previous 1,000 words first.
Instantly, yes.
That is crazy.
It is. But as long as your original instructions remain inside that active window, the statistical prediction for the next word will remain anchored to your topic.
Okay, that makes sense.
But, the context window has a hard limit. If the conversation gets so long that your original prompt falls out of the back of the window, the model will start to drift.
Because it just forgets.
Because it literally can no longer see the original goal. It has no long-term memory outside of that specific window.
That makes perfect sense. But that brings up like a really fundamental problem. If LLMs are just generating text by predicting tokens, how do they actually process the meaning of our prompts to begin with? I mean, they don't understand English, they don't have brains, they just process math.
They absolutely just speak math. And this is where we have to explore the concept of vector embeddings.
Okay.
This is really the bridge between human meaning and machine mathematics.
Wait, you're going to have to lose the jargon for a second?
Yeah.
How does a word like carburetor or puppy become a math equation? Like, who decides what the numbers are?
The model decides during its training. So vector embeddings are the process of turning text into a very long list of numbers.
Okay.
Imagine you want to define an animal using just numbers. You might create dimensions. Dimension 1 is how furry is it? Dimension 2 is how domestic is it? Dimension 3 is how big is it?
Right.
So a dog scores high on furry and domestic and, medium on big. A wolf scores high on furry, big, but very low on domestic.
Okay, so I have a coordinate for a dog and a coordinate for a wolf.
Exactly. Now, AI models do this, but instead of 3 dimensions, they use thousands of dimensions. Thousands. The model trains on massive amounts of data and learns which words and phrases tend to appear in similar contexts. It assigns coordinates based on those relationships.
I see.
And the brilliant part is that items with similar meanings are assigned numbers that place them physically close to each other in this massive mathematical space.
So just to use a special analogy here, imagine a giant map of ideas. Dog and puppy are cities right next to each other on this map.
Right.
Wolf is maybe a city in the next state over. But carburetor is like on another continent entirely.
That is a highly accurate way to visualize it. And to actually use this map, we need vector databases.
Okay, what are those?
These are highly specialized systems designed to store and quickly search through millions of these embeddings. When you type a question, the system converts your question into a mathematical vector, places it on that map, and asks the database which stored vectors are physically closest to this query vector.
Oh, which is why this is so much better than old school keyword search.
Exactly.
Like if I search my company's internal database for how do I leave the company, a traditional keyword search is just literally looking for the word leave.
Yep.
And if the employee handbook only uses the phrase termination policy, the search just fails.
It finds nothing.
Right. But semantic search using embeddings can successfully match my question with the document titled termination policy because their meanings, their actual coordinates, are located right next to each other on that meaning map.
Right. It captures the intent rather than just matching vocabulary. However, you have to be careful because this system has a notable vulnerability. We call it the false friend failure.
Ah, right, 'cause I was just thinking, just because two things are close to each other on a map doesn't necessarily mean they agree.
You hit the nail on the head. Embeddings only map relevance, they do not map truth or logic.
Oh, wow.
For instance, think about the phrases is allowed and is not allowed.
Okay.
They're used in the exact same context, discussing the exact same rules in the exact same types of documents. Because they appear in similar environments, their coordinates map very closely to one another.
That's hilarious, but also terrifying.
Hmm.
It's like searching a medical database for how to cure a headache, and the AI confidently hands you a document titled How to Cause a Headache just because the words map closely on the grid.
That is exactly the risk. The vector database retrieves them because they are highly relevant to your question, but they mean the exact opposite thing.
Wow.
This is a primary reason why AI models can sometimes give you very confident but entirely incorrect answers.
Okay, so if the map just gives us related stuff, how do we stop the model from lying to you? How do we ground it in actual facts? Because the February articles explain that we combine these vector databases with generative models in a workflow called RAG,
Yes, RAG, retrieval augmented generation.
retrieval augmented generation.
Yeah.
It is a fundamental shift in how we use language models.
Mm.
Instead of asking the model to answer a question by relying solely on the vague patterns it memorized during its training, RG introduces a mechanical two-step process.
Can you break down those two steps for me? Like, what is the software literally doing behind the scenes?
Sure. Step one is retrieve. You ask a question. The system searches a vector database to find documents relevant to your prompt, just like we discussed with the meaning map.
Got it.
Step two is generate. The software invisibly intercepts your prompt before the AI even sees it.
Invisibly intercepts it.
Yeah, it pastes the text of the documents it just found into your prompt and adds strict instructions. So the software literally invisibly types something like, uh, ignore everything else, just use the following paragraphs to answer the user, and then it just pastes the retrieved information.
Precisely. It attaches them to your original prompt, heavily reducing the need for the model to guess. The model just reads the provided text and summarizes it for you.
So it's essentially an open book test. Instead of answering from memory, the AI gets to look at the textbook.
Yes, exactly.
But wait, why not just paste the entire corporate textbook into the invisible prompt every single time? Why bother searching at all?
Because of the context window limit we discussed earlier.
Oh, right.
You cannot feed a 1,000-page library into a model's prompt. It just won't fit, and the model would lose track of the instructions anyway. Therefore, documents must be split into smaller pieces before they are stored in the database. This is called chunking.
Chunking. And the site's February guide emphasizes that chunk size is this massive trade-off.
It really is.
Because if you cut your documents into very small chunks, say a sentence or two, your search retrieval will be highly precise, but you completely lose the surrounding context.
Right.
But if you use large chunks like several pages, you keep the context, but the
Yeah.
retrieval gets noisy because you are pulling in a lot of irrelevant text.
And beyond just size, you risk splitting important ideas right down the middle.
What do you mean?
Well, if a chunk mentions a complex legal term, but the definition was in the previous chunk, the model gets confused because it only receives the second half of the thought.
Oh, I see. Wait, how do you fix that? Do you just have a human read through and cut the documents perfectly at the end of every paragraph?
That would take way too long. Instead, automated systems use overlap. They ensure that chunks share some text at the boundaries.
Okay, how does that work?
For example, chunk 1 might contain sentences A, B, and C. Chunk 2 will contain sentences C, D, and E.
Ah, so C is in both.
Exactly. By overlapping sentence C, they ensure key ideas aren't accidentally sliced in half.
Okay, so RAG is giving the AI an open book test with perfectly overlapped chunks of information. But if the system hands the model the wrong page of the textbook, the model will just confidently write down the wrong answer, won't it?
It absolutely will. RAG still fails. The generative model is just following instructions. If the retrieval step fetches the wrong chunk, or, a chunk with an outdated 2022 policy, the model will faithfully generate an incorrect answer based on that bad data.
Or it might just completely misread the page it was handed.
Yes, that too.
Hmm.
The model might creatively misinterpret a perfectly correct chunk. It might read a policy that says an expense is usually covered and confidently tell the user that it is always covered.
Oh, man.
Yeah. RAG reduces guessing, but it is definitely not a guarantee of truth.
So RAG gives the model a way to look up information. It can read, but reading isn't doing.
No, it's not.
If I want the AI to actually book my flight or calculate my taxes or update my database, how does it physically press the buttons?
Well, it doesn't press buttons. This brings us to giving AI hands through function calling and agents.
Okay.
This is where we move from a chatbot that just talks to a system that executes tasks. But it is vital to understand that the model itself cannot execute anything. It starts with function calling.
Let me clarify that because I think it's a huge misconception. The model itself isn't opening a calculator app or searching a live database.
Right.
The model just outputs a highly structured line of text. It basically writes a command that says, I need to use the calculator tool with the numbers 4 and 5. The surrounding software, the actual application running the AI, sees that text request, pauses the AI, runs the calculator itself, gets the number 9, and feeds that result back into the AI's prompt.
Exactly.
The model is just the planner. The tool does the actual work.
That is exactly how it works. And
Yeah.
when you string several of these tool use moments together in an automated loop, you get an AI agent.
Oh, okay.
An agent is not a single hyper-intelligent brain working in the background. It is a system loop. The loop is plan, act, observe, update.
I love this analogy for it. It's like a manager and an intern. The LLM is the manager delegating tasks. It says, plan. I need to find the user's account. Act. Use the database lookup tool.
Yes.
Then it observes the result from the intern. Ah, the database says the account is locked. Then it updates its plan. New plan. I will draft an email to the user explaining the lock. It gives the AI multiple chances to try a tool, read the result, and refine its approach.
It is a really powerful workflow, giving the illusion of autonomy, but it introduces entirely new failure modes. An agent might make the wrong tool choice entirely,
Like what?
like trying to search the public web for a user's private account detail instead of checking the internal docs. Or it can suffer from what we call step drift.
What is step drift?
It is when the model gets so caught up in a sequence of tool calls that it completely loses track of the user's original goal.
Oh no.
Yeah, it falls down a rabbit hole of its own planning and just forgets what you actually asked it to do in the first place.
Wow. And what happens if the model just misreads the output from its own tool? Like if the calculator returns a complex equation, but the AI just misunderstands the numbers.
Then the entire plan derails. If a tool returns a complex result, the LLM still has to summarize and interpret it correctly. If it misreads the result, it will update its plan based on a false premise.
That sounds chaotic.
It can be. Another major failure is the inability to admit when it lacks sufficient information. A good human intern would stop and ask the manager for clarification.
Right.
But many of these models are heavily biased toward providing an answer, so they just guess the missing parameters and execute a flawed action.
Which is exactly why these setups require massive guardrails, because these systems are now acting, not just talking. You need strict software rules regarding permissions.
Absolutely.
You can't just let an agent permanently delete a database because it planned to do so. Guardrails are the hard-coded limits outside the AI that say this specific tool requires human confirmation before executing.
Right. You must bound the system's autonomy. You are essentially putting physical fences around what the manager is allowed to instruct the intern to do.
Okay, so we've talked about text, math, lookup, and action. Let's look at the final piece of the puzzle. We've explored how models process language, search for meaning, and use tools. But how does this exact same underlying concept learning patterns and predicting continuations apply to generating art and sound? Let's talk about going beyond text.
It is fascinating because the underlying philosophy remains the same, even though the medium changes. Take image generation.
Okay.
When you type a prompt for a picture of a dog, the model does not imagine a picture the way a human artist does. It translates your words into internal numerical signals. It has learned through vast amounts of training data which visual patterns correlate with which word patterns.
So it literally turns static noise into a picture step by step.
Yes.
Like it starts with a screen of random pixels, and those mathematical signals guide it to gradually arrange the pixels until they form the visual shapes associated with the coordinate for dog.
Exactly. It is a mathematical diffusion process. And this is why image editing is actually much harder than generating an entirely new image from scratch.
Really, why?
Because image editing is controlled generation.
Oh, because the model has to balance so many constraints. Like, if I have a photo of a person and I ask the AI to change the shirt they're wearing, the model can't just generate a whole new picture.
Right, it can't.
It has to preserve the original background, preserve the person's face, preserve the lighting, while simultaneously altering only the requested object to fit the prompt. It's juggling multiple mathematical constraints all at once.
Exactly. It has to freeze certain parts of the math while changing others. Now, apply this pattern matching concept to music generation. An AI does not hear raw sound waves the way a human ear
It
does.
doesn't.
No, raw audio data is too massive and messy. Instead, the audio is compressed into internal units or tokens, very much like the text tokens we discussed earlier.
Oh, wow. So it's just predicting the next audio token based on the statistical patterns of the genre I asked for. Like, it learns that in jazz, the pace tends to be a certain way. It learns how texture builds or how energy rises before a chorus.
Yes.
But this leads to something really interesting mentioned in the February guide called the loop problem. Can you explain that?
Yeah, the loop problem occurs because the AI is excellent at predicting what should happen in the next 3 seconds, but it completely lacks long range musical design.
Okay.
It doesn't know where the song is going in minute 4. It has no overarching structural intent, so it often gets stuck repeating the same local patterns over and over.
It's like a composer who only has a 3 second memory span. They can write a beautiful chord transition, but by the time they finish it, they forgot what the start of the song sounded like, so they just play the same transition again.
That's a perfect way to describe it.
Which brings up a really profound point about art. When an AI song makes you feel sad, is it just because it mathematically learned that slow tempos and certain chords historically make humans cry?
Yes. That is exactly it. The AI replicates the structural patterns that trigger human emotion, the minor chord progressions, the swells, the acoustic space, without actually feeling anything itself.
Wow.
It has successfully mapped the acoustics of sadness, but it has absolutely no understanding of the human experience of sadness.
That is wild. It's just learned the exact sound patterns that trigger human neurological responses.
Man, as we look back at all the topics we've covered today, I think the biggest takeaway is how much our understanding shifts when we look at the actual mechanics.
It really does.
Mm,
And to briefly synthesize the journey for everyone, AI models aren't magic brains. They are pattern matchers operating within much larger systems.
right.
Whether we are talking about vector embeddings, mapping the coordinates of meaning, RG systems invisibly pasting context into a prompt, or agents looping through external tools, these are mechanical statistical workflows.
Just really fast math.
Yeah. And understanding these mechanisms helps us treat AI as a set of useful tools with highly predictable limits, rather than treating them as flawless authorities.
Absolutely. And before we go, think about this. If AI agents are now being given hands to execute tasks using external tools, and they still suffer from hallucinating facts, misreading data, and step drift, we are rapidly approaching a world where we have to manage software the exact same way we manage an unpredictable human intern. Are we ready to be middle managers for machines? If you want to keep learning, the full February 2026 guide is available at howaimodelswork.com.